Okay, this is a cute little thing. We have discussed already various colors of hydrogen, for example, when it's naturally available from, ground like oil. We call it the white hydrogen. Green hydrogen is when you use catalysis, let's say, or sorry, electrolysis of water to break it into hydrogen and oxygen with green energy. That's called green hydrogen. And there are various other colors: blue hydrogen, yellow, gray, etc., etc., right? So we have a similar thing for carbon as well, as you can imagine. So I wanted to just include it since it's something we should know, because not all carbon is the same. And it matters because now carbon is everything, and we are having this course, this entire discussion about climate change. Everything we can do about it are all about carbon, mitigation, adaptation, and the impacts, and so on. The colors of carbon, then, this is a little review from Nature Reviews, Earth and Environment, very short article. Let's just read it. It's a bit old, 5 years. A full spectrum of color-based descriptions has emerged to describe the properties and distribution of organic carbon: black, brown, red, blue, green, and teal. There are a few more that the US Geological Survey has reported that we'll look at. This color-based terminology contributes to our evolving understanding of the carbon cycle by moving past traditional broad classification of carbon types, often as simple as inorganic versus organic carbon. Then we have dissolved, particulate, and so on, to more nuanced definition based on carbon function, attributes, and location. Those are the definitions that tend to be, quite broad, and those are the traditional ones. For example, some of the colors, blue, green, and teal, highlight the role of carbon in climate change mitigation via sequestration. Other types, black, brown, and red, impact Earth's heat balance or promote cryospheric melting. So there is the energy balance impact of carbon, and then what we do about it by hiding it somewhere, right? Like capturing and sequestering red carbon. Red carbon is the newest color in the carbon spectrum. In its broadest context, it includes all living biological particles on snow and ice that reduce albedo to survive. It describes Roman Dial, professor at Alaska Pacific University. That's his comment. Red expresses a common pigment produced by snow microorganisms, but the term also encompasses pigments spanning yellow through to purple. These colors absorb abundant green and blue wavelengths of light, melting the snow and ice and producing liquid water necessary for life, and freeing up nutrients such as nitrogen and phosphorus that are bound within ice crystals. So it's a cute evolution, right? They can go and somehow find their way on ice, or end up freezing when season changes or snow falls and so on. But they have managed to evolve to use sunlight to melt the glacier around them, or ice, to survive and procreate, and so on. So this is again added by Dial. The comment about how they produce nutrients by melting ice. Although the red carbon moniker has not yet caught on, the impact of reduced albedo from the pigments is known to increase snowmelt, as seen in the Arctic, motivating increasing research into the role of microorganisms and the cryosphere. Black carbon, one of the best known colors of carbon, also reduces snow and ice albedo, thus increasing melting, and along with brown carbon is produced through the incomplete combustion of organic matter. Some of the production is natural, such as during wildfires, but fossil fuel burning and industrial activities are the major sources as well. So, all the fossil fuels are hydrocarbons. In comparison with black carbon, which is often described as graphitic and absorbing a wide spectrum of light, brown carbon is the visible and UV light absorbing component of organic aerosols. However, Both of these terms change with advancing technologies. For instance, black carbon was initially identified visually, but now Alan Ruffel, professor at the University of California, Irvine in the USA, notes that there is a spectrum of carbon from char produced by partially burning biomass and soot by the burning of fossil fuels. Similarly, a multitude of organic compounds, including some that are produced by secondary processes in the atmosphere, have been identified within the umbrella term brown carbon. What is clear for both carbon types is that in addition to reducing air quality, they absorb solar radiation at the top of the atmosphere, retaining heat and impacting climate. Yeah, recent interest in using biochar as a way to store carbon, as stated by Ruffel, has led to broader research of black carbon for climate change mitigation, casting its dark carbon in a more positive light. Okay, so you know how things change. We've talked about this in a different context already. Here are some graphic for images to help. Left to right, Getty images, so you can see various colors of carbon here. So just to give you a sense of the colors of carbon. Carbon sequestration has sparked interest in green, blue and teal carbon. These colors are united by describing the occasion of the carbon rather than an inherent physical property. Green carbon reflects the carbon sequestered by the land system, okay, and this is in the water, I suppose. This is stated by Carlos Duarte, professor at the King Abdullah University of Science and Technology, known as KAUST in Saudi Arabia, and this incorporates carbon in soils and within biomass such as forests. Blue carbon, by contrast, describes the carbon sequestered in the ocean, adds Duarte, the definition of which originally focused on mangroves. Okay. Mangroves, salt marshes and seagrasses, but now also includes seaweed and sediments more broadly. Lastly, teal carbon, which has only recently entered the carbon color nomenclature, relates to the carbon stored in inland freshwater wetlands, says Siobhan Fennessy, professor at Kenyon College in the USA. Sequestration of blue carbon especially has interested policymakers and environmental scientists as a solution for climate change mitigation because, as Duarte states, it has no negative impacts, contributes to adaptation by raising the seafloor and buffering waves, providing additional benefits such as enhanced fishery resources, and is cost effective. Okay, there are additional considerations as well. Blue carbon can also act as, increasing oxygen in the water is already mentioned as buffer to storms and waves, and cleans the water, etc. Fennessy argues, though, that inland sites are needed to be recognized for their ability they have to build carbon stocks. This is even more vital in light of the recent changes of the WOTUS rule, the Water of the United States rule, which may allow the destruction of inland wetlands that were previously protected. If destroyed, the teal carbon stored in the wetlands could act as a CO2 source. There are a lot of changes in the US now in terms of what climate change is and what needs to be done for it, and so on and so forth. I always keep saying so on and so forth, but I don't seem to be able to get rid of this habit. Anyway, defining and effectively using terms such as these here can motivate the advancement and advocacy of carbon research, especially when as Duarte states, the demand for sound, effective and value-adding nature-based solutions for climate change mitigation is growing. These carbon colors are living definitions, though, that cross disciplinary boundaries and are expanded and refined to adapt new knowledge, instrumentation and policy needs. Moreover, new carbon colors continue to emerge, as seen in the case of red and teal. As carbon research moves forward, one wonders what the next color of carbon rainbow will be. So let's look at the infographic from the US Department of Interior and US Geological Survey. Colors of the carbon rainbow. Not all carbon is the same. Scientists use color to classify carbon at different points in the carbon cycle based on carbon function, characteristics, and location. This creates a more descriptive framework than traditional organic and inorganic carbon labels. So here is C6 carbon with a mass number of 12.011. Okay, what is purple carbon? Carbon captured through the air or industrial emissions. Blue carbon is of course stored in ocean plants and sediments. Teal is carbon stored in freshwater and wetland. Carbon stored in freshwater and wetland environments. Green is of course carbon stored in terrestrial plants, as we mentioned. So they are corresponding to this part of the rainbow here. If you move further, you have red that we mentioned already, carbon released through biological particles on snow and ice that reduce the albedo and lead to melting. Carbon released by incomplete combustion or organic matter, or incomplete combustion of organic matter is known as the brown carbon. Carbon released through industrial emissions is gray, and black of course is the carbon released through the burning of fossil fuels. So we don't see much gray and black in or even brown in rainbow colors, but anytime you have a spectrum of light, you can call it a rainbow, right? So just a brief introduction, and it's an interesting topic. As we said, these colors will keep increasing in number based on classification, but let's just accept the argument that this will help with the overall idea of dealing with carbon in the decarbonization, as well as where am I going with this, as well as studying the carbon cycle, studying the fate of carbon sources, sinks, and generally how to deal with it in the mitigation business, and nature-based solutions. That's an important part, right? If nature-based solutions can provide a lot of co-benefits with sequestering of carbon, then knowing their colors can help bring that into general colloquial languages, and politicians can hang on to them and take decisions as well. Okay, let me leave it here.